Hello, welcome to class. It's Friday, April 17th, about a month away from the AP test. So, a few things. Hopefully, you've watched through the short little video talking about grades and things like that. I'm sure a few of you still have some questions. So, I'll just go through those again real fast. So, probably the biggest things are just the fact that we just have one big grading cycle for the entire fifth and sixth grading cycle. So that's just going to be one big grade book, everything from a little bit before spring break to the end of the year. Um, all of your grades have been turned into homework grades, even all of your tests. Um, and we can only do 2 assignments per week. So I know we have more assignments than that. The big assignments I'm counting for this week and next week are going to be tests and labs. So, like the spring break test, the simple harmonic motion lab, and then next week I'm counting the mock test and simple harmonic motion test. So obviously we have more assignments than this in Google Classroom. Still, please try to do them. I'm trying to keep them to where they're a reasonable length. And as long as you do these, I'm adding points elsewhere. So if you've been following along and doing all your work, your grade should be probably better than it's been all year. If it's not, tell me. If you're not feeling like your work is being rewarded, I really want to know. I'm trying to reward it, but I can't tell if you're unhappy with it if you don't tell me. So if there's anything that you're unhappy with, please let me know. You don't have to tell me right now. Send me an email. Just say something. I'll try to correct it. Um, but yeah, hopefully you're happy with your grade. Um, the other thing is just please keep trying to do these, even if your grade is good. This year it is a really short AP test, 2 questions. It sounds like most of it's going to be writing. So you never know. They might ask about topics that you feel really comfortable with. You have a unique chance to get a really high grade on the AP test. So just just keep working with it, keep trying, and I think everything should be all right. So it doesn't look like people have any other questions on that. Um, so yeah, let's just get into it. I only gave you one question a day, so it's Friday. Figured I wouldn't put you with too much, and then you're probably still working on the mock test. So we'll go through this one. And next class, we're going to try something a little bit different. So I'll put this up right after this class, and you can look at it. It's going to be ranking tasks, so a little bit of a shift. All right. So let's go through. We'll look at the question. So this one, we have a rod right here. We have a pivot stuck in place. We have a rod sticking out and a disc sliding towards it at a certain speed. Let's make sure we look at the variables. So one thing that could be easy to mix up is this distance d versus this distance x. So let's be kind of careful with those. All right, so here we have the left end of a rod of length d, rotational inertia I, attached to a frictionless horizontal surface. So it's on a horizontal surface, so we're looking down from above. Notice top view. So this is sliding along a frictionless surface towards this rod. Frictionless pivot, so no friction, that's all good. Point C is the midpoint, the center of the rod, so this is where the center of mass of the rod is going to be. The rod is initially motionless, so this thing begins at rest, but it's free to rotate about the pivot. So, first of all, what should our thoughts be immediately going to? We have a pivot stuck in place, but this thing is free to rotate. Immediately, what should we be thinking this problem is asking about? Like, what quantities are going to be conserved and what quantities aren't? Well, free to rotate, it's a good chance we're talking about some form of rotational motion. And I titled this rotation, so I mean, hopefully that's kind of obvious. So free to rotate without friction. So that's looking like maybe rotational kinetic energy, maybe angular momentum. We have that stuck pivot point. So because this pivot point is stuck in place, we're probably not talking about linear momentum. This is going to collide and then spin, but it's not going to keep sliding upward. So because this can't keep sliding, that means we're probably not talking about linear momentum. Um, the student slides a disk of mass m disk towards the rod with velocity v naught perpendicular to the rod. The disk will stick to the rod. So that's pretty important, sticking to the rod. So these are going to stick together in elastic collision. So that just eliminated using conservation of energy. So an elastic collision means energy is going to be lost. So we're probably not even using rotational energy. So this looks really quickly like we know this is going to be an angular momentum problem. So free to rotate, collides and sticks. So in inelastic collisions, we need to use some form of momentum, can't slide. So we're probably going to have to use angular momentum. So even before you've gotten to some questions, we probably know where this question is going. It hits a distance x from the pivot. That's another important thing to kind of look at. X is how far the disk is from the pivot point, and d is the entire length of the rod. So let's make sure we keep these variables separate in our mind. They look very similar, d and x, but d is the length of the rod, x is how far we are from the pivot, how far the mass, the disk, slides and hits from the pivot. All right. The student wants the rod disk system to end up with as much angular speed as possible. So after the collision, we want this thing to rotate as fast as we can possibly go. So suppose the rod is much more massive than the disk. Now, this is just a nice approximation to pretty much say that the disk doesn't contribute to the rotational inertia. So I don't need to include the mass of the disk in the moment of inertia formula, which is kind of a nice approximation. So to give the rod as much angular speed as possible, should the student make the disk hit the rod to the left of point C, at point C, or to the right? So in the chat, vote left, at, or right. See a right. See a left. So we want it to either hit to the left is over here, at C here, or to the right over here. So this is the pivot. This is like the hinge of a door. If we open a door, where do we open the door at? Probably not going to open it at the pivot. Normally we put door handles over here away from the pivot, so we open it and swing it around this way, right? So we probably want it somewhere over here in order to open this, right? If I want to open a door, I push as far away from the hinge as possible. So it's probably going to be to the right. And now this is one of those ones, again, a lot of times it's you get the points without answering this. So if you're certain that your answer is true, select it. If you're not certain, it's better off not to select it. So if you have that question mark, like maybe this, I wouldn't check one of them or I wouldn't select one of them. And then I would just write what I know. All right, so it is going to be to the right of C. To the right. And then it says briefly explain without manipulating equations. So we're not going to calculate. So you've lost your formula sheet. I did post a link to it. Just Google it. Go to Google. So AP Physics 1 formula sheet. Should be one of the first things that pops up. And then, yeah, it's the very first thing, just the secureMediaCollegeBoard.org. And it's the exact same formula chart we have. I put a link to it also on the mock exam. So if you have a printer, you can print it out or put it on your iPad or phone, or I think you have an iPad. So either one of those. So if you have a printer, this would be a good thing to print out. I would definitely have this printed out for the AP test when you take it, and then write everything you know about all of these, like when we use formulas and all of that. So I guess I could pull this up more often as I'm going through it. All right, so we want to explain why we want to hit to the right of C. So yeah, going back to our formula chart, well, we want to use something dealing with rotation. Well, all of our rotation equations were kind of in here, kind of towards the bottom on the left-hand side. So we want to deal with something that's hitting to the further to the side. Well, that's probably something dealing with radius. Well, torque. Torque is the thing dealing with radius. So that's probably something I could start with. It says don't manipulate equations, but it never says don't use equations. So I can start with that torque equation. Torque is going to be how far we hit this thing times the force times sine of the angle. Well, if you notice, this is going to hit at a 90-degree angle, and sine 90 is just 1. So it's really just radius times force. So what we're really looking here is we're trying to get torque. So I want a large radius. Large distance from the pivot gives a large torque. All right, so that's only part of this. We want to end up with the greatest final speed. So that's only my torque. I get a big torque if I have a larger radius. But then I can relate torque to my angular acceleration, right? Angular acceleration is net torque divided by moment of inertia. So we're not manipulating equations, but I can still write this. So angular acceleration is net torque divided by moment of inertia. And then this moment of inertia, the whole point of that is of saying that the mass is really small. The disk has a small mass relative to the system. All that's saying is that I don't need to include the mass of the disk when I'm talking about this. So my moment of inertia for the rod doesn't change when the disk collides with it. So that means all I have is my net torque. My net torque went up. So large net torque means larger angular acceleration. And a larger final angular speed. So if the bigger torque gives a bigger acceleration, means this thing is going to end up going faster at the end of everything. And I usually write a little bit more than I have to. I'm pretty sure this doesn't ask for all of those. So yeah, it's just 1 point. So correct answer to the right of C. So notice this is one of those ones reasoning cannot earn credit if the incorrect selection is made. So this is one of those ones where if you selected the wrong one, you can't earn the points. But if you don't select something, you can. So this is why I'm saying only select the correct answer if you know it's correct. So if you're uncertain whether it's correct or not, or you're just guessing, I wouldn't select something. But if you really know the answer, I would select it. So an explanation that the torque exerted on the disk or the angular momentum of the disk is greater when further from the pivot. So I chose to go with the torque route. It hits at a larger distance, so it has a bigger torque, so it's going to have a bigger acceleration, so it's going to go faster at the end. But you could have also related this to angular momentum. So you have a bigger angular momentum when you're further from the pivot, right? That's the whole thing about angular momentum for a point mass. Was the radius times mass times velocity of that point mass. So if you have the same mass and speed, a bigger radius gives you a bigger angular momentum. By the way, since you do have open notes, this is one of the equations I would write on your formula chart. Along with the other ones, how the angular displacement times radius is equal to the distance traveled or angular distance. You could also have your angular speed times radius is your tangential speed, and your angular acceleration times radius is your tangential acceleration. Other things to write on that formula chart. All right. So then we get to B, a person just looking up random things on the internet and assuming they're true. They find a speed for the post-collision angular speed omega of the rod. So they have this equation. Angular speed is the mass of the disk times x. So again, this is where we need to be careful. Your AP test, it doesn't sound like there's going to be a lot of math, but they could easily give you an equation like this and ask you if that equation makes sense. So we have this final angular speed mass of disk times x. So x is how far the disk hits from the pivot, not to be confused with the length of the rod itself. Okay, times the initial speed divided by moment of inertia. So regardless of whether the equation is correct, does it agree with your qualitative reasoning from part A? In other words, does the equation for angular speed have the expected dependence as reasoned in part A? So looking back at part A was asking where we need the disk to hit in order to get the greatest angular speed, which means we're talking about this x value. So the whole thing of this is saying, does the A make sense? A is talking about the distance from the pivot, and the distance from the pivot is represented by x. So pretty much all this is asking is, does this x value make sense where it is in the equation? And for whatever reason, I can't select just the x. Whatever, just the x value. So does that x value make sense where it's at? Yes, why yes? It is yes. So we only care about that. Directly proportional with the angular speed. Yeah, pretty much exactly true. So the equation shows that as x goes up, the distance mass hits from the pivot. Not mass, let's be specific. They call it the disk. The distance that hits from the pivot goes up. Final angular speed goes up. So that's what the equation shows. And that's what we said in part A. In part A, comma, we said as radius goes up, the final speed goes up. And that means the equation matches the reasoning in part A. And that's a bit more than you really need, but just something kind of relating it, because they asked, does the equation match what we said in part A? So something saying the equation shows as that distance, the disk hits from pivot, the angular speed goes up because it's in the numerator. So x in the numerator. And you don't have to use fancy words. You can just say x is on top in the fraction. Therefore, as x goes up, final angular speed goes up. And then we said in part A that the further we hit from the pivot, the faster we end up going. So that means the equation matches our prediction in part A. And my computer will not shut up about saying I need to restart it for the update. So the correct answer is yes. So here is something where if you selected the wrong, so if you selected no, you can still earn full credit if you made the incorrect selection in A. So this is one of those weird ones where if you messed up in A, so if you said to the left of C in part A, and then you matched your explanation that no, my equation doesn't make sense, and you correctly said it doesn't make sense because it doesn't match what you said in A, you can still get those 2 points. So if you said the wrong thing in A and then you explain why the equation doesn't make sense compared to that, you can still earn full 2 points. But here, so the first one is your selection is consistent. So if you got the correct answer in A, then you had to select yes, and just for selecting yes, you got a point. This is one of the few times you can just select an answer and get a point. And then again, if you selected left and said no, you got the point. And then for indicating the equation shows that angular speed increases with that distance from the position. And yeah, as long as you related it to that. So far, I think these are mostly straightforward. Now C, again, another thing that could show up. By the way, this is a QQT type question. Like I've been talking about qualitative, quantitative translation. You are going to get a question like this, and this is going to be the first long question, a 25-minute question, where they ask qualitative, if I change something, how does the other thing change? Same thing here, same thing here. And then quantitative, where you have to actually go through and give a quantity and do some math. And then translation, if I were to change something, how would another thing change? So this is a question. This is the type of question you're going to get on the AP test. So see, another student deriving the equation for the post-collision angular speed omega of the rod makes a mistake and comes up with angular speed equals moment of inertia times the distance the disk hits from the pivot times the initial speed of the disk divided by the mass of the disk divided by the length of the disk squared. Again, D is how long the disk is. Let's not confuse length of the disk with how far, length of the rod with how far the disk hits from the pivot, I mean. So without deriving the correct equation, how can you tell this equation is not plausible? In other words, that it does not make physical sense. So physical sense, anytime it's asking, does this make physical sense? It's not asking, do the units match up or anything like that. It's saying that one variable on here is doing something really wrong. Like mostly it's either in the numerator when it should be in the denominator, or it's in the denominator when it should be in the numerator. So briefly explain your reasoning. So there's a few things we can do here. Which variables are wrong? There's 2 big ones. Mass. So mass of the disk is wrong. And that moment of inertia. Yeah, both of these are wrong because this is moment of inertia for that rod. So either of these are good. So equation shows more massive disk, right? So it's showing mass of the disk in the denominator. So that's showing if I have a more massive disk, because it's showing angular speed proportional to 1 over mass of the disk. So as that goes up, angular speed goes down. So that's showing a more massive disk results in a slower final angular velocity. But that doesn't make sense, right? If I slide something with more mass, this thing is obviously going to spin faster. So, however, more massive disk has more angular momentum. So you don't necessarily have to put this in terms of angular momentum, but it has more angular momentum, and that means the rod should rotate faster. Or just anything like saying, if I slide a more massive disk, the rod should obviously rotate faster. So that's one thing. The other one is the moment of inertia. So the equation shows as that moment of inertia for the rod gets bigger, right? This is in the numerator. As the moment of inertia for the rod goes up, final angular speed goes up. However, that moment of inertia for the rod is going to resist the angular acceleration. And that means a larger moment of inertia for a rod is going to mean a slower final angular momentum. And again, it's kind of important to say what the equation shows and what it should show. So don't just say the equation shows this. Say for mass of the disk, the equation says that if I have a more massive disk, the rod is going to rotate slower. But this makes no sense. If I slide a more massive disk, obviously it's going to collide and end up going faster, right? I mean, I think this is one of the more obvious statements. Like, if a fly runs into your car, it's not going to move. If a train runs into your car, it's going to move. More mass is going to lead to more final speed. And then the moment of inertia is very similar to mass. So moment of inertia is how much this thing resists angular acceleration. So if that rod has a really big moment of inertia, it's hard to turn. So it's going to turn more slowly after the collision. Small moment of inertia means that it should rotate more easily. All right. And then for focus on functional dependence instead of considering units or dimensions. So that's pretty much what we're all talking about. Big mass of the disk means big angular speed, or big moment of inertia should mean small final angular speed. So focusing on that instead of units and dimensions. So that's where it's talking about, what was the wording again? Physical sense. So physical sense, they're caring more about, are the units in the correct spot, as opposed to does the equation make sense? Like, do the units go through? And then for addressing mass of the disk or moment of inertia or both, and then as long as you addressed it, you get a point. So if you just said mass of the disk is wrong, you got a point. If you just said moment of inertia is wrong, you got a point, just for even saying that. And then for concluding the equation is wrong because of the dependence on mass of the disk, moment of inertia for both. And then so any of that going through talking about what the equation shows, what it should show. And then obviously they always give these examples. And try to make your own worded examples. Don't just copy these. That's not helping you at all. But yeah, if the disk has a larger mass, then you have more angular momentum. So the rod gains more angular momentum, which should make this go faster, but the equation shows the angular speed is decreasing because you have a bigger mass of the disk because it's in the denominator. Something like that. And by the way, if we go through and do the units for all this, it actually ends up being correct units, even with that distance to the fourth. That's another reason they're not wanting you to focus on the units instead. So far, so good. Anyone have any questions on A through C? A through C are the points where I think you should be able to get those kind of easily. Maybe not like super easily, but those are where most people are earning their points before we get to D and E. And these are also the types of questions, again, I expect these to be more the types of questions you show up on the AP test. It doesn't sound like there's going to be a whole lot of math and deriving formulas because it would be really hard to type those. So these are the ones to get kind of good at practicing on. And then D is that quantitative part of this. So you probably are going to have to do math. I doubt there's going to be absolutely no math, but it's probably going to be pretty straightforward math, like just rearranging simple equations, like where you just have to kind of add and subtract variables. That's just my prediction. Or it's going to reduce down to a more simple answer. But yeah, even if you're typing up your answer, which I think you should, it sounds like they really want you to type up your answer. It's going to be geared towards typing it. You should still have scratch paper. So you should still have some paper off to the side that you can write things down, write out any math you have to real fast, things like that. All right, now for D and E, now we're not assuming the rod is much more massive than the disc. Now we're assuming that when the disc collides and sticks with the rod, the two are going to rotate, and so the disc is going to contribute to the moment of inertia. All right, so immediately before colliding with the rod, the disc's rotational inertia about the pivot is mass of the disc times the x squared, so how far the mass hits the disc from the pivot. And its angular momentum with respect to the pivot is mass of the disc times the initial speed of the disc times how far the disc is from the pivot when it collides with the rod. So that's nice. We're not having to derive these. They just gave it to us. Like, again, rotational inertia, they're probably going to give this to you. That's not a thing you need to know. All you need to know is rotational inertia is some sort of mr squared. So we want to derive an equation for the post-collision angular speed omega of the rod. Express your answers in terms of distance, mass of the disc, moment of inertia, distance from the pivot, and the initial speed of the disc, and any physical constants as appropriate. Probably not going to have something as in-depth math on this, but I don't know. I can't see the future, so I could see them trying to do something more math-intensive, so I might as well go through and practice this. So again, what concept are we using to solve for the final angular speed? What's being conserved during this collision? Not total mechanical energy. What's keeping mechanical energy from being conserved? That's a good guess. But what happens? There's a key phrase in here. Yeah, sticks to the rod. So this is an inelastic collision. So we are losing mechanical energy to heat and sound. Even though there's no friction, when we have a collision where things stick together, you are losing energy. So not mechanical energy. So that's out. But we have another thing that can be conserved. What's conserved during an inelastic collision? Momentum. And then, yeah, specifically, it's going to have to be angular momentum, the thing that's stopping momentum. And I was just looking for the word momentum, by the way. But yeah, we have a pivot here that's stuck in place, so this can't keep sliding along. So we are losing our linear momentum. We're losing our translational momentum. Again, if we look at a big enough picture, then this is attached to the Earth, and the momentum of the disk is going into the Earth itself, but we're not including the Earth as part of our system. So it's not going to keep sliding, not free to slide, so linear momentum is not conserved, but this does collide and rotate. So this thing is free to rotate without friction, so our angular momentum is going to be conserved. So we are going to have to use conservation of angular momentum. Again, very similar to momentum. I could see them just asking you to set up this equation or saying what's conserved, but we do know angular momentum is conserved. So total momentum before the collision equals total angular momentum after the collision. So I have angular momentum for the rod before the collision plus angular momentum for the disc before the collision is all equal to angular momentum for the rod after the collision plus angular momentum for the disc after the collision. Angular momentum, forget, is this L value right here, moment of inertia times angular velocity. Again, if you've lost this formula chart, I would suggest printing it out and writing all over it and having that for your AP test, nothing stopping you. All right, so I have moment of inertia for the rod times the initial angular velocity for the rod plus moment of inertia for the disk. Actually, they gave us angular momentum for the disk before, so I'm just going to leave this as angular momentum for the disk initial. Is all equal to moment of inertia for the rod times the final angular speed of the rod plus moment of inertia for the disk times the final angular speed for the disk. Which of these do we know are zero? Which thing starts or ends at rest? Well, they're both spinning after. Yeah, so the rod initial, this thing begins at rest. It starts at rest. It's not rotating. So this starts with no angular momentum. I know the angular momentum for the disk initially. It just tells me that is mass of the disk times the initial speed of the disk times x. So that's good. This whole thing was just given to us. That's nice. What's the same for both of these after the collision? They collide and stick. So they have the same final angular speed. So the final angular speed of the rod is equal to the final angular speed of the disk. We can just call that final angular speed. Moment of inertia for the rod, final angular speed, plus moment of inertia for the disk, final angular speed. So I could just factor out the final angular speed. So just like an inelastic collision, I would add the two masses together, mass of the disk plus mass of the rod. Instead of mass, we have moments of inertia for rotational. But again, really, really similar to an inelastic collision, just mass plus mass times final speed, moment of inertia plus moment of inertia times final angular speed. It looks a little scarier, but it behaves the same. Mass of the disk is the initial speed, not is, times the initial speed times the distance from the pivot point. Then I have the moment of inertia for the disk. It's just I, not I, moment of inertia for the rod is I, but moment of inertia for the disk is that mx squared. And I guess it is mass of the disk. Plus moment of inertia for the rod is just I times final angular speed. Then I can divide this over here. Mass of the disk times the initial speed of the disk times the distance of the disk from the pivot when it collides, divided by mass of the disk times the distance of the disk from the pivot squared during the collision, plus moment of inertia for the rod is all equal to the final angular speed. So probably not going to have a question like this where you have to derive something completely like this. But I could easily ask them, like, see them giving this in terms of other things that are a lot easier. Like, if they had the same moment of inertia, I could easily see them asking something like that, because then all of a sudden this reduced down to, if they just said this as a moment of inertia L, and then you have I plus I times final angular speed, I could easily see them asking you something like that, where L is this divided by 2I. I could easily see them wanting you to plug something like this in, typing that out. So it might not look like this, but I could easily see this turn into something where they do have you type in something pretty straightforward. All right, questions on that? Let's see the points. So using conservation of angular momentum, so you can't talk about linear momentum. You had to actually talk about angular momentum. Linear momentum for the disk and rod is not conserved. So as long as we set up an expression for angular momentum at one point, which is as much as just sum of Li equals sum of Lf. If you wrote that, you got a point. Indicating the initial angular momentum of the system is equal to mass of the disk times the initial speed times x, which I would say is what I did here whenever I said this was 0. And so this is the initial angular momentum. For a dimensionally correct expression for the post-collision angular momentum, that includes moment of inertia for the rod times final angular speed. So dimensionally correct, as long as you got like I omega plus I omega, something like that, you get the point. And then for getting the rotational inertia is just the sum of the two rotational inertias. So you just add the two moment of inertias together to get the total moment of inertia. So just like mass, it's a scalar. You can just add these things together. All right. I don't know why I just put that down. Final question, final part of this one. Now consider the collision for part D was derived, except now suppose the disk bounces backwards off the rod instead of sticking to the rod. Is the post-collision angular speed of the rod when the disk bounces off of it greater than, less than, or equal to the post-collision angular speed of the rod when the disk sticks? So I've asked this question a bunch of times. You also just saw the key. So when this bounces, faster or slower? Less than is definitely the thing that everyone goes towards, and I think that's why they asked this question. That's probably the most common answer. But let's look at this. So we know our angular momentum is conserved, right? So our total angular momentum before is equal to our total angular momentum after. So because of this, all I have is my rod and my disk. So these are the two objects I can play around with. So if I have my angular momentum total has to be constant, is going to equal to, I could say this is my change in angular momentum for the, let's say this. Let's say my change in angular momentum is 0. Angular momentum total is 0. So that means however much my change in angular momentum for the rod, however much this changes is going to be equal to the change in angular momentum for the disk. So however much angular momentum this loses, this one gains. Or vice versa. If this gains angular momentum, the rod loses angular momentum. If the disk loses angular momentum, the rod gains angular momentum. Well, the moment of inertia isn't changing, so I could really look at this as moment of inertia for the disk times the change in angular velocity for the disk. So we have our two cases. They go along, they collide, and they stick together, or they go along and the disk hits and bounces back. Which one of those gives a bigger change in angular speed, or just bigger change in speed? And not speed, velocity. Bigger change in angular velocity. The one that bounces back, right? So let's say the one that goes, and if it sticks, so let's say something goes, it sticks, it goes, collides, and then it keeps going forward after it sticks. But the bounce is going to go this way, it's going to hit, and then it's going to bounce back. So let's say this one goes from like 2 to 1. The change in velocity is just going to be -1, or you can just look at magnitudes and call that 1. But let's say this one's going at 2 and then it bounces back at 1. What's this one's change in velocity, or at least the magnitude? It goes from 2 to 0, and then 0, it bounces back. So this is actually a -1. So how far is -1 from 2? 3. Yeah, I didn't say it bounced back the same. But yeah, so if you bounce back, you have a bigger change in velocity. And another way of kind of imagining this, so let's say we have two cases. You're walking towards me, and I like shove you, and you just slow down. You have you have a change in velocity, but it's kind of small. This other case, you're walking towards me, and I run at you, and I tackle you, and you launch back the other direction. Which one of those are you going to feel more? The one where I just like shove you to slow you down, or the one where I have to like shove you and send you flying backwards? Like, you're definitely going to feel the one that sends you flying backwards a lot more than the one that just slows you down, right? So it takes a lot more to make something bounce backwards than it just does to make it slow down or stop. Because here I could slow you down and stop you, but here I would have to slow you down, stop you, and send you back the other direction. Does that kind of make sense, or? We'll keep going. Well, this is all kind of a tangent over here. So when we're talking about this, so let's kind of put this all into words then. So it is going to end up being greater than. So if this thing bounces back, it's going to be greater than. So we're still talking about rotation. So I'm still going to be talking about angular momentum. So I'm going to say the magnitude of the change in angular momentum for the disk is going to be equal to the magnitude of the change in angular momentum for the rod. So if the disk bounces back, then it has a greater change in angular velocity and a bigger change in angular momentum. So because this has a bigger change in angular momentum, the disk has a bigger change in angular momentum. Well, however much angular momentum the disk changes by, the rod has to change by the same amount in order to keep our angular momentum conserved. So if the disk has a bigger change in angular momentum, that means that the rod also has a larger change in angular momentum and therefore rotates faster. And this is that real big difference between velocity and speed. So this is also kind of a vector question about how sending something backwards is a lot bigger change, because we're talking about vectors that care about the entire distance from the positive number all the way to the negative number, as opposed to speed, which doesn't care forward or backwards or anything like that. So let's see here. So correct answer, greater than. So for indicating either directly or by analogy to linear case. So I talked about angular momentum, but they're okay with talking about linear momentum here. So if you were just saying the words momentum, that should be fine. I'll get to TME for in a second. So the disk's angular momentum with respect to the pivot changes more in the bouncy scenario than the original scenario, or in similar argument in terms of impulse. So it would be something about how the disk bounces back, so it has a bigger change in angular momentum, or you would say it has a bigger change in angular velocity, so bigger change in angular momentum. So you have to describe what's happening to the disk. So the disk has a bigger change in speed, so a bigger change in angular velocity. And then talking about conservation of angular momentum. So this would be saying that the angular momentum is conserved, so showing how one value goes down, the other one goes up. Or I was using more of a momentum impulse, how the change in angular momentum for one is equal to the change in angular momentum for the other, or the rod gains more angular momentum because the disk changes angular momentum by a greater amount. So here's in the bouncy collision, the disk has more angular momentum in the clockwise direction to keep the system angular momentum constant. The magnitude of the rod's counterclockwise angular momentum must be greater than before. Or just something about the disk bounces back, so the rod has to have a reaction in the other direction more, just something like that. Mechanical energy, I don't think you would get the point for mechanical energy here. A problem with mechanical energy is you don't know how much energy is lost. So it's going to be a lot more messy. You can't really use energy unless you know a little bit more about the amount that's lost. And even when you're trying to use energy, you're going to have to relate it back to momentum. So I would say no points for mechanical energy in this case. So it would have to give you something indicating that it's an elastic collision. If they had said something about this being elastic, then you get that point. But just because something bounces doesn't make it elastic. So yeah, you wouldn't get points from using energy on this one. Any other questions? And yeah, that's part of the reason I only gave you one. I expected going through this one to take a lot more time, especially with angular momentum. I feel is one of the weaker points for the majority of people. So this is one of the ones that's a 12.1, but this was also another one of those really rough ones on students. I think the average points for this one was like 2.6 out of the 12 points. So if you got 3 or more points, then you're doing above average. I mean, it's not the best, but this was a tricky question. That's good that you got more points than expected. I mean, your goal for getting this one, you're trying to get a 40%, 0.4 times 12. So you're trying to get 5 or more. So if you did 5 or more on this, you're on track to passing the AP test. The other really good thing about this, again, I don't expect them to ask a really long question like this about angular momentum because they're going to be trying to cover all of the topics. So there's a good chance the angular momentum aspect of a question on this year's AP test would just be one of the parts. So if you get to a question like this, I would skip around. There's a good chance they're going to ask about a lot of other topics that aren't angular momentum so that you can get some points and they can actually test your knowledge. So don't stress so much if you didn't do as well in this one and you're thinking, oh man, I'm going to get an angular momentum question and just absolutely get destroyed by the AP test. I don't think they're going to do that to you. I think if they ask you a question like this, it would probably be something where maybe the angular momentum question doesn't happen till the very end and they find some way to ask other questions up here that are more directly applied to other things. So any other questions on this one? Is everyone okay? All right. Well, as long as you keep working on these, they're not all going to show up as a grade in the grade book, but I am going to keep putting in points elsewhere. So it should be good. It should be helpful for your grade. So just please keep trying to do these. Keep working on them. It will be beneficial. But yeah, and then next class we'll do something a little bit different. It's going to be ranking tasks. I'm actually going to post that right now if you want to go look at those. But other than that, have a good weekend and feel free to stick around and keep asking questions after I stop recording.